In this video, I'm going to talk a little bit about science, what science is, and we're also going to talk a bit about how information is gathered to build on our knowledge base of science. So first of all, what is science? Well, science is knowledge. It's a body of knowledge that's been gathered through many different and difficult experiments over time. But it's more than that. Science is also a process of acquiring knowledge. This is referred to as the scientific method, which you may have heard of. So it's through this method that we gather knowledge, and we sort of build up over time more and more knowledge, as well as techniques and things like that that allow us to progress as a modern society. So let's talk a bit about the scientific method. So it has a number of steps, and as we go through the steps, I'll use the example of a situation in which you have a broken remote for a TV. So the first step is to observe and generalize. So let's imagine you come home, you pick up your remote, it doesn't work. Okay. So based on previous knowledge with electronic devices, not just remotes, but any sort of electronic device, you know that they either have to be plugged in or they need a battery of some sort. And there are even some devices that need both, okay? But so you're going to, essentially you'll have this observation, okay, the remote doesn't work. That's the first step. And you're going to pose a question, what's wrong? Okay, so that's very natural, what's wrong? And then you're going to think about what you've experienced in the past, and you're going to use a form of reasoning called inductive reasoning. Now, that's a very fancy term, but it's something you've been doing your whole life, inductive reasoning. What is it? Well, one form of inductive reasoning involves generalizing from a specific example or examples to some sort of general idea. So at this point in your life, you've experienced, batteries going dead and electronic devices not working. So you're essentially doing inductive reasoning. You don't own every single electronic device in the world. That's not really possible. But based on your knowledge, you understand how these devices work. They need to have a working battery. So you generalize from this knowledge that you have, and you say, well, look, this is probably what's happening here. Probably the battery's dead. Okay, so that leads us to the next step, which is number 2, formulate a hypothesis. A hypothesis is a tentative statement about the natural world. So in this case, we would say the batteries are dead. So it's as simple as that. It's just a positive statement. The batteries are dead. That's the hypothesis. Now, it's a little bit more complicated in the sense that, okay, you can pose a hypothesis as a simple positive statement like that. The batteries are dead. But there are some requirements for a hypothesis. It must be testable. This means that it's possible that it can be proven wrong. So it's something that you can actually test and potentially support it with some data, or you could potentially prove it wrong. So if you make up a hypothesis and there's absolutely no way to test it, then it's probably not a scientific hypothesis. Now, there's a little bit of exception in the sense that sometimes scientists will come up with hypotheses, and we don't have the tools yet to answer the question, but maybe in 10 years or 50 years, those tools and that equipment will be there to test the hypothesis. So it still could potentially be scientific hypothesis, even if we don't have the current technology to test the hypothesis. But at least potentially it should be something that could be testable and proven wrong. And the next thing I'm going to say is going to sound a little strange, but scientists never prove a hypothesis. They never say, look, I've proven this hypothesis, okay? That's the sort of dialogue you might see in a movie that's not very well written. Scientists are much more cautious. They say the data support the hypothesis. So they'll talk using these words, and it sounds like, okay, so scientists are just not very confident. They're not confident people. No, that's not the case at all. The reason that they say this is really there's no logical way that you can absolutely prove a hypothesis. There may always be some alternative explanation. So for that reason, they're a little cautious with their wording, and they say, look, the data support the hypothesis. So in this case, let's imagine, we'll go on to the next step and we'll see what happens. Let's go on to the next step here. Okay, so the next step is, and this is a little bit confusing, but the next step is make a testable prediction. And most people are going to say, well, didn't we just do that with the hypothesis? Well, the prediction is a little more specific than a hypothesis. The hypothesis is fairly general. The prediction is going to be more specific, and it really gives you the tools to then test the hypothesis. So if we were, let's go away from the remote control example, for a second, because that one's almost too simple, right? Let's imagine that you have a drug, and it's a drug for high blood pressure. It's going to counteract high blood pressure, also called hypertension. And so their hypothesis might be that drug X, let's call it drug X, will reduce blood pressure in people. And, that's a good thing. It's going to help people with hypertension, with high blood pressure. Now, that's a hypothesis. The prediction is going to be much more specific. We're going to say, well, if we give a certain dosage of this drug and we give it for 2 months to this certain type of patient, then we will see a reduction in their blood pressure. So you see, it's much more specific, and you're almost saying exactly how you're going to test it, essentially, right? By the time you've written out this prediction. So predictions, one way to identify a prediction is they're often use deductive reasoning, and they're often stated as an if-then statement. So deductive reasoning, we talked about inductive reasoning a second ago, and one form of that is generalization. Here, deductive reasoning is essentially in the form of an if-then statement. So if a patient with this condition takes this drug at this dosage for this period of time, then we'll see their blood pressure drop, right? That's a prediction. It's an if-then statement, and that's using deductive reasoning. Okay, the next step is experiment and observe. So the idea is that you'll plan out this very careful experiment in which you've carefully, everything's controlled for, and then you execute this manipulation, excuse me, in which you change something like the dosage of a drug. You might give patients different dosages of drugs. Let's go back to the example we were using, though, a second ago with the remote control that wasn't working. We have a hypothesis, the batteries are dead. So what's our prediction? Well, the prediction is a little more specific. It's going to be if new batteries are put in the remote, then it will work. Okay, again, this is a very simple sort of example, so there's not a tremendous difference between the hypothesis and prediction here. Okay, so then we do the experiment. We replace the batteries. Okay, now there's potentially different outcomes. If you put the batteries in and the remote works, then the data support the hypothesis. Okay, so we don't say that we prove the hypothesis and again, the reason is because logically we haven't really proved it. It's possible that just by jiggling things around, there might have been a loose wire, and that loose wire is now back in the right position, and that's why the remotes are working. It had nothing to do with the batteries. Now, we can go a step further, right? We could do a further experiment in which we get a little battery tester, and we test the old batteries, test the new batteries, and so forth. So we could do yet another experiment, essentially, to see if, our hypothesis, if we can support a hypothesis or not. So you can see that there's potentially multiple rounds of experimentation. I mean, most likely you would just stop at this point, right? You'd say, okay, the remote works, I'm done. Now, there's another possibility. Let's say you put the batteries into the remote control, it doesn't work. Then we say the data do not support the hypothesis. So it appears that, let's imagine the battery, that the batteries are good because they're new batteries, or perhaps you tested the batteries before putting them in with a battery tester. So in this case, it really doesn't appear that the batteries were the problem. So we're going to have to revise the hypothesis. So maybe come up with a new hypothesis and prediction. So you might say, well, look, maybe there is something wrong with the wiring within the remote. If I open it up and I sort of jiggle things around, maybe I'll get it to work again. So you can see this could go on, right? You could have a series of hypotheses, new predictions and experiments and so forth until you get the remote control working. Okay, so this is the example I've used is sort of a toy, simple example, very, very simple with remote control, but it's logically not that different than being a doctor or a scientist or someone trying out a new treatment on patients or something like that. So we're going to stop there, and we'll pick up this idea, and we'll talk a little bit more about how drug trials work and so forth in the next video.